Welcome to the Analytical Scientist's new video application notes with Marks International. This video application note is called Enhancing the Development of Low-Emitting Products and Materials with Caroline Widdowson. Before we begin, please allow me to quickly introduce Caroline. Dr. Caroline Widdowson is the Product Marketing Manager for Thermal Desorption at Marks International, a specialist manufacturer of analytical thermal desorption instrumentation, associated sampling equipment, and time-of-flight mass spectrometry. Caroline participates in many standards and regulatory committees, including CEN, ISO, ASTM, and BSI, and works closely with industry, test labs, and research institutes to equip and advise on analysis of VOCs and SVOCs. Caroline, over to you.
Thank you, Richard. Today we're going to talk about how we can utilize microchambers and thermal desorption GCMS to produce low-emitting products and materials. There are multiple sources of volatile and semi-volatile compounds that affect the indoor air quality of either a home or a work environment. Consumer products and building materials are increasingly subject to regulations limiting the release of these chemicals into the atmosphere. In addition, consumer awareness to the potential health risks is driving the demand for a reduction of emissions and an improved assessment of these products and materials. These standards and regulations cover a wide range of products and materials. In Europe, the Construction Product Regulation stipulates mandatory VOC testing and quality control of products used inside the home: carpets, paints, adhesives, sealants. In America, it's not legislative, but voluntary needs to comply with green building codes. Specific product standards are also implemented for products that are seen as problematic, such as spray polyurethane foam. More recently, consumer goods such as air fresheners, toys have also been implemented under VOC emission testing standards. Most of these certification standards are very time-consuming. Typically, you would place a piece of material into a 1 meter cube chamber for up to 28 days before you can take the test. These long protocols for certification create a need for rapid assessment, both for the manufacturers to understand how they can comply with these different regulations, to reanalyze their formulation, to do troubleshooting, and to screen and predict how these materials are going to work. Also, test laboratories like to pre-screen their materials before submitting for a long-term test. And this is where we utilize the microscale chamber, a rapid dynamic headspace unit. The sample is placed inside one of the chambers, a flow of gas is applied, and the organic vapors are then swept onto a sorbent tube. That sample tube is then desorbed in a thermal desorption instrument, and the sample is then passed through to the GCMS for the analysis stage. The microchamber thermal extractor is a standalone emission screening device. And once the material is placed inside, one of two types of sampling can be taken place. Either a bulk sample, in which we're looking at a microgram per gram or a microgram per meter cubed emission rate, or we can raise the sample up inside the chamber, sealing the edges and the base so that only the emissions from the surface are measured. And this would give us a specific emission rate, a microgram per meter squared per hour. We can place different types of sample tube onto the outlet of the microchamber, sorbent tubes for volatiles and semi-volatile analysis, or DMPH cartridges for formaldehyde analysis, followed by HPLC. Typically, if we're testing materials that are placed inside the home, we would test at room temperature to simulate a real-world environment. However, if we're testing materials that perhaps are used inside a vehicle or in other environments, we can increase that temperature to simulate those parameters. So let's look at a couple of examples of how we can use this type of sampling and analysis. One of the first things we can do is compare formulation processes. So we can compare the emission profile, and here what we have is an uncured adhesive on the top and a cured adhesive on the bottom. And what we can see is that during the curing process, we reduce the amount of octane within our sample and increase those long-chain hydrocarbons. And what this allows a manufacturer to be able to do is to determine how long a curing process should occur for and give instructions to reduce then the volatiles that would be measured from a final product. Another use of this type of technology is comparing with a competitor's products. You can take your own product and a competitor's product, place it into the microscale chamber, sweep the volatiles and semi-volatiles from it, and analyze it using thermal desorption GCMS. This can be used for many different reasons. One, to be able to determine whether your customer's products, your competitor's products, are very similar in formulation to yours, or whether you would like to then change your formulation to specify to another customer's requirement. In this third example, we're looking at 3 different processes for the same formulation on flooring tiles. And what we have here is a resilient flooring material. We cut out our samples, we make them to the exact diameter of the microscale chamber, we place them inside, but we raise the sample right up to the top of the chamber. When the lid closes down on top of the sample, there's a baffle that comes down and creates a defined surface area. And what this means is that when we sweep our volatiles that have been emitted, we're only getting what's emitted from the surface material, nothing from the sides and nothing from behind. So here we have 3 different samples. All of them are the same formulation. The first one, sample 1, has no lacquer on top of it. The second sample has a lacquer, and the third sample has the same lacquer but has also undergone a heat cycle process. Here we can see the 3 GC traces of the samples, and what we have are 3 very similar chromatograms showing what's inside the sample. If we look a little bit closer, what we can do is analyze these against each other. And here's the data in a different format. And what we can tell from this data is that the lacquering process reduces the amount of phenol within a sample, and also the amount of 2-ethyl hexanol. It also reduces the BHT. However, interestingly, when the heat process is applied, that increases slightly. We can see that the lacquer is responsible for the odorous emission of butanoic acid, but it's completely eliminated after the heat cycle. And this type of information just really gives manufacturers the capability to understand how their formulation processes can affect the emission profile of their materials, and subsequently how that can help them comply with certain regulations and standards. In addition to these quality control procedures, you can also test the raw materials, you can compare emission profiles across a range, and you can pre-screen products before third-party emission tests, comparing products with competitive materials, and allowing yourself to develop new, low-emitting, higher-value materials within the research and development part. So I'd like to thank you for your attention today. There are more details on this application on the Marks website. This is application note 103, and please feel free to look on the website for more details. Thank you very much for your time.